Hi everyone, myself Praveena. I am the Assistant Professor of Mathematics in Institute of Aeronautical Engineering College. Today I want to discuss about the topic on diagonalization of a matrix. It comes under Module 2 in Matrices and Calculus subject. Okay. Already we know that. What about diagonalization of a matrix? Simply, what do you call diagonal matrix except the diagonal elements remaining all are zeros? Okay, that is the definition of the diagonal of a matrix. Through the concepts for any matrix, for any square matrix, we have to reduce as diagonalization of a matrix. Okay, here we have to discuss the concept of diagonalization of a matrix, how to reduce the matrix as diagonal through the concept. Okay, here diagonalization of a matrix. Here one theorem is there. According to the theorem statement, if a square matrix A of order n has n linearly independent eigenvectors x1, x2 and so on xn corresponding to the n eigenvalues lambda 1, lambda 2 and so on lambda n respectively. Then a matrix P can be found such that P inverse AP is a diagonal matrix. This is one of the statement for the diagonalization of a matrix. If AB is a square matrix of order n has linearly independent eigenvectors. What are the eigenvectors? x1, x2 and so on xn. How you got that eigenvectors corresponding to the eigenvalues of the given matrix B? That matrix P can be found such that P inverse AP as multiply P inverse A into P as a diagonal matrix. Okay, from that we get directly the given matrix as diagonal. Okay, from that, what about the proof for that? Here, for that I am taking, what about the given statement? In the given statement, they are given x1, x2 and so on, x and b, the eigenvectors of A corresponding to the eigenvalues lambda 1, lambda 2 and so on, lambda n respectively. And these eigenvectors are linearly independent. Define P is what? P is the given vectors x1, x2 and so on xn as the eigenvectors. Since the n columns of P are linearly independent. What is linearly independent? If determinant of P is not equal to 0, we have to consider that matrix as linearly independent. Okay. Hence, P inverse exists. Consider AP is equal to A into x1, x2 and so on xn. Okay, from that AX1, AX2 multiply inside the brackets with A, that is AX1, AX2 and so on up to AXN. Okay, here what is A matrix? We have to consider that given corresponding eigenvalues, write it as that is lambda into x, lambda 1 into x1, lambda 2 into x2 and so on, lambda n into xn. For that x1, x2 and so on, and I'll write it as that lambda 1, lambda 2 and lambda n as one matrix form, that is lambda 1, 0, 0, 0, lambda 2 and so on 0, 0, 0 and so on lambda n. That is equal to, I'll write it as this matrix as P and this is D. Once observe here we get except diagonals remaining all are zeros. For that I'll write it as P into D form, where D is equal to one diagonalization of a matrix. Once observe here, that is AP is equal to P into D form. Okay, here we have to multiply both sides with P inverse AP equal to P inverse P into D. That is P inverse A into P is equal to P inverse P into D. That is P inverse AP is equal to, this is equal to I into D. That is D. That is diagonalization of a matrix. From the given conditions, from the get here one diagonalization of a matrix from the condition of P inverse A into P. Therefore, here the theorem is proved. Okay, from the condition, what about the statement? if a square matrix A of order n has linearly independent eigenvectors x1, x2 and so on xn corresponding to the n eigenvalues lambda 1, lambda 2 and so on lambda n respectively, then a matrix P can be found such that P inverse AP is a diagonal matrix. Okay, this is the proof of that. Okay. Next, model and spectral matrix. What is model and spectral? If you know the basics only, we get easily diagonalization of a easily we can get the diagonalization of a matrix. For that, first of all, we have to discuss the basic concepts of the model and spectral matrix. The matrix P in the above result, which diagonalize the square matrix A, is called matrix of A, and the resulting diagonal matrix D is known as spectral matrix. Okay, the matrix P in the above result, which diagonalize the square matrix, which is diagonalized that before the matrix is called as the model matrix. Once observe, for the given matrix, they are given any square matrix. Okay, given any square matrix. For that we have to find eigenvalues and find that corresponding eigenvectors. For that square matrix as 3 by 3 means for that we get 3 eigenvalues lambda 1, lambda 2 and lambda 3. For that eigenvectors also we get x1, x2, x3. Okay, we get that 3 eigenvectors, write it as one matrix form. This matrix is called as model matrix. After getting that eigenvectors, we have to write it as one matrix form. That matrix is called as model matrix. This is the concept of the diagonalization of a matrix. What about that? First, write it as one square, given matrix as square matrix. For that, we have to find eigenvalues and eigenvectors. And for that eigenvectors, okay, write it as one matrix form. Then matrix is called as a model matrix. Okay, we have to assume it as P. Okay, for that, find out next step, that is find P inverse. What is P inverse? Adjoint P by det P. And after that, after getting that P inverse, okay, multiply P inverse A into P, we get a diagonalization of a matrix. This D is called spectral matrix. This D is called spectral matrix. This is the concept of the diagonalization of a matrix. Once again, I discuss. Okay, for any they are given a question square matrix form. For that, we have to find out eigenvalues, and for the corresponding find eigenvectors. Write it as that eigenvectors as one matrix form. That matrix is called as, we have to assume that matrix as P. That matrix is called as model matrix. For that, find P inverse and multiply P inverse with A into P. Okay, then it is this is converting as the diagonalization of a matrix. This D is called as spectral matrix or diagonal matrix. Okay, this is the concept of the definition of the model and spectral matrix. Once observe what about the basic definition here. The matrix P in the above result, which diagonalize the square matrix A, is called model matrix of A, and the resulting diagonal matrix D is known as spectral matrix. Okay, this is a model matrix and this is spectral matrix. Okay, note here the important concept. If x1, x2 and xn are not linearly independent, this result is not true. Okay, here we have to observe the given eigenvectors are not linearly independent. For that case, the given matrix is may or may not be diagonalizable. Okay, that is the first one. Suppose, second point, suppose A is a real symmetric matrix with n pairwise distinct eigenvalues lambda 1, lambda 2 and lambda n, then the corresponding eigenvectors x1, x2, xn are pairwise orthogonal, hence P is equal to E1, E2 and so on En. This is one condition. Where E1 is equal to x1 by norm x1, E2 is equal to x2 by norm x2 and En is equal to xn by norm xn. Then P will be an orthogonal matrix. Okay. Hence, for that, next concept, calculation of powers of a matrix. Okay, already we discussed what about the concept of the diagonalization of a matrix. For that, sometimes they are asking the calculation of the powers of a matrix. For that, what about the concept? We can obtain the power of a matrix by using diagonalization. Let A be the square matrix, then a non-singular matrix P can be found such that D is equal to P inverse A into P. Okay, D is equal to P inverse A into P. Okay, for that, what about this is D? What about D square? P inverse A into P inverse A into P. Here multiply both P inverse A into P inverse into AP. That is P inverse A square into P. Since P into P inverse is equal to I. Similarly, D cube is equal to P inverse A cube into P. In general, what about D power n? P inverse A power n into P. Here we have to observe A square A cube and here they changed P inverse A power n into P form. To obtain A power n, pre-multiply 1 by P and post-multiply by P inverse. Then P into D power n into P inverse is equal to P into P inverse A power n into P inverse. For that we get directly what about A power n? P into D power n into P inverse. Therefore, what about A power n? P into D power n as the diagonalization of a matrix multiplied with P inverse. From that we get directly A power n. Okay, A power n is equal to P into lambda 1 power n 0 0 and so on, 0 lambda 2 power n 0 0, 0 0 0 lambda n power n into P inverse. Sometimes they are asking after the diagonalization calculation of the powers of a matrix. Further, what about the formula? This is the formula. A power n is equal to P into D power n into P inverse. Okay, this is the concept of the calculation of a matrix. Okay, before going through that, once again I'll repeat the topic. What about the diagonalization of a matrix? For the given square matrix, okay, find eigenvalues and eigenvectors. Write it as that eigenvectors are here lambda 1, lambda 2 and lambda n 3 and so on, and that corresponding eigenvectors are x1, x2 and so on xn, and that corresponding, write it as one matrix form, that is x1, x2 and so on up to xn. This is called as model matrix. This is called as model matrix. For that D is equal to, okay, for that we have to find P inverse, and after that D is equal to P inverse multiply P inverse A into P form. Okay, here what about D? This is called diagonal matrix or spectral matrix, or this is spectral matrix, diagonal matrix or spectral matrix. Once observe, this is the diagonal matrix. Here observe, what about the diagonal elements in the diagonal matrix? Here that corresponding eigenvalues only we get the diagonal elements in the diagonal matrix. For that case only our answer is correct. Okay, after getting the answer in the after getting the answer, for that diagonal elements are equal to what? That corresponding eigenvalues. If the two are equal, then our answer is correct. That is the concept of the diagonalization of a matrix. After getting that, after that sometimes they are asking calculation of powers of a matrix. What about the formula for that? A power n is equal to P into D power n into P inverse. P power n is equal to P into D power n into P inverse. What about P? That is model matrix, and P inverse is that inverse of the given matrix, and D power n as the powers of the diagonal matrix. Multiply these. This is the calculation of A power n. Okay. Once observe here, after getting this diagonalization of a matrix concept, okay, here two cases are there. Okay, here diagonalization of a matrix also two types are there. If the eigenvalues are repeated and if the eigenvalues are distinct. If the eigenvalues are distinct, okay, if the eigenvalues are distinct, the given matrix definitely diagonalizable. That is definitely diagonalizable. Okay, if the given eigenvalues are distinct, so that definitely that is diagonalizable. So no need to worry about that. Continue the concept of reducing the matrix as a diagonalization matrix through the conditions of the problem. Okay, here if the eigenvalues are similar, for that case, the given matrix may or may not be diagonalizable. If the eigenvalues are similar, for that case, the diagonal matrix may or may not be diagonalizable. For that case, we have to verify algebraic multiplicity and a geometric multiplicity. If the two are equal, definitely the given matrix is diagonalizable. Okay, if the two are not equal, then the given matrix is not diagonalizable. Before proceeding the answer, after getting the eigenvalues, if the given eigenvalues are distinct means for that case definitely it is diagonalizable, so that we have to continue the procedure. If the diagonal eigenvalues are similar, for that case first of all we have to verify AM and GM. If the two are equal, then we have to proceed the concept of the diagonalization. If the two are not equal, then directly write down the given matrix is not diagonalizable. Okay, these are the main two cases in diagonalization of a matrix. Now I want to discuss about the first case if the eigenvalues are distinct. Okay, now I want to discuss with the first question with eigenvalues are distinct. Okay, right. The first question: determine the model matrix P of -2, 2, -3, 2, 1, -6, -1, -2, 0. Verify that P inverse A into P is a diagonal matrix. Okay, here we have to determine the model matrix. What about the model matrix? Indirectly, what they are asking in the question. Okay, verify is it diagonalization of a matrix or not. Okay, model matrix means after getting the eigenvector, we have to write it as one matrix form, that is called as a model matrix. Okay, here given one P matrix, for that we have to verify is it diagonal or not. Okay, for that what about the first concept? First of all, we have to verify the given matrix is square matrix or not. Here this is the 3 by 3 matrix. This is 3 by 3 matrix, that is -2, 2, -3, 2, 1, -6, -1, -2, 0. The given matrix is square matrix. Okay, what about the first point of the diagonalization of a matrix? For the given matrix, first of all, we have to find the eigenvalues. For that, what about the definition for finding the eigenvalues? For that, first of all, we have to write it as one characteristic equation form. What is that characteristic equation? Modulus of det A minus lambda I is equal to 0. Okay, here what about A given matrix and what about I the corresponding identity matrix or unit matrix. For that here write it as -2, 2, -3, 2, 1, -6, minus 1 minus 2 0 minus lambda into 1 0 0 0 1 0 0 0 1. Determinant of. Okay, after subtracting with the 2, write it as minus 2. Okay, minus into minus lambda, lambda into 1, minus 2 minus lambda. This is 2 minus 3. 2 minus 0, 2. 1 minus lambda, 1 minus lambda, minus 6 minus 0, minus 6. Next, minus 1 and minus 2, and the next one 0 minus lambda. Okay, for that, okay, this is the characteristic equation form. For that we have to find, okay, determinant of the given matrix. After determinant of the okay, from the after finding the determinant, we get one equation form. What is that equation form here? That is lambda minus 5 into lambda plus 3 whole square is equal to 0. For that, once observe here, we get thus the eigenvalues are, okay. For that, here we get two eigenvalues. Thus the eigenvalues are here, which gives lambda minus 5 and into lambda plus 3 is equal to 0. So that here, what are the eigenvalues for that? Here we have three eigenvalues for that. Here lambda is equal to 5 and lambda is equal to minus 3 and lambda is equal to minus 3. So that here, what about the eigenvalues? Three eigenvalues for the given matrix, that is 5, minus 3 and minus 3. For that, if lambda is equal to 5, that is distinct eigenvalue. Okay, for that we have distinct eigenvalue. So that here minus 3 and minus 3 are the repeated eigenvalues. Okay, once observe, is it here we get distinct eigenvalues or similar eigenvalues? One is distinct and another two are, okay, similar eigenvalues. Therefore, here which one is similar? Minus 3 as similar. Therefore, that algebraic multiplicity is equal to how much? 2. Okay, na? For that we have to find that corresponding eigenvectors. If the eigenvectors are, we get that two eigenvectors for the similar eigenvalue. So that if the two are equal, then we get the given matrix as the diagonalization of a matrix. One is distinct. For the distinct, no need to verify algebraic multiplicity and geometric multiplicity. But here we have to find the similar eigenvalues, algebraic multiplicity. Here similar eigenvalue multiplicity as am is equal to 2. Okay, for that now I am finding that the three eigenvalues corresponding eigenvectors. After that I am finding the geometric multiplicity. If the two are equal, after getting that eigenvectors, the given matrix is diagonalizable, or else directly write down after getting the eigenvectors, algebraic multiplicity is not equal to geometric multiplicity, so that the two are not equal, so directly that is not diagonalizable. Okay, actually I want to discuss about the distinct eigenvalues, but unexpectedly here from this question we get similar eigenvalues. So that I am discussing about the similar eigenvalues diagonalization of a matrix. Already I discussed what we discussed. For the similar eigenvalues, we have to verify algebraic multiplicity and geometric multiplicity. Okay, for that, first of all, if lambda is equal to 5, okay, what about the first eigenvalue? Lambda equal to 5, that is minus 7, 2, minus 3, 2, minus 4, minus 6, and minus 1, minus 2, minus 5. Okay, once observe, this is what about a minus lambda I? This is a minus lambda I. In that we have to substitute 5. In that we have to substitute 5. That means minus 2 minus 5, that as minus 7. And next remaining, no need to change, 2 minus 3 as it is. That is the first row. And second row, first element as 2 and 1 minus 5, that as minus 4. And the next element is minus 6. That is minus 6. And next second row, third row, minus 1, minus 2, 0, minus 5, that is minus 5. So that after substituting lambda is equal to minus 5 in the matrix, okay, that is A minus lambda I into X is equal to 0. This is the formula for finding eigenvectors. For that already we know that A minus lambda I form. In that we have to substitute lambda is equal to 5. For that we get directly this matrix, that is minus 7, 2, minus 3, 2, minus 4, minus 6, minus 1, minus 2, minus 5. And what about X matrix? That is the unknown matrix. Here I am assuming that I unknown matrix as x, y, z, that is minus 7, 2, minus 3, 2, minus 4, minus 6, minus 1, minus 2, minus 5 into x, y, z is equal to 0, 0, 0. Okay, for finding eigenvalues and eigenvectors, already we discussed in the previous classes. Same concept here we have to apply. Okay, from that we get directly eigenvectors for the corresponding eigenvalue of lambda is equal to 5. Okay, for that, what about the concept after writing as this? I'll write it as one. Okay, here after getting this, okay, reduce the matrix as echelon form. Okay, reduce the matrix as echelon form. Easily we can get the unknown values of x, y, z. For reducing the echelon form, what about the concept? Okay, only we have to apply the row operations. Okay, we have to reduce the matrix as upper triangular. Okay, we have to reduce the matrix as upper triangular. Already we discussed this topic in the first module, echelon form and normal form. Here I am applying the echelon form for reducing the matrix as echelon with respect to the row operations. For that, here I am applying the row operations for that, that is minus 7, or else here I want to change the rows. Before going through that, I want to change the rows. R1 interchanges to R3. Okay, for our convenience, or else directly also we can apply the row operations, no problem. But our convenience for the multiplication purpose, I want to interchange the rows. Okay, that is minus 1, minus 2, minus 5, 2, minus 4, minus 6, minus 7, 2, minus 3 into xyz is equal to what? 0, 0, 0. For that, apply the row operation with respect to R1, that is R2 tends to R2 plus R1, and the next one R3 tends to, okay, R3 plus minus 7 R1. Okay, from that I'm reducing as a matrix. I'll reduce it as the second one and the third element as zeros. That is minus 1, minus 2, minus 5 and 2 plus, here one observe, okay, this is wrong, R2 plus 2R1. This is R2 plus 2R1. For that, this is 0, and here minus 4, minus 4 and minus 4, this is minus 8, and next minus 6 and minus 10, that is minus 16. Similarly, with respect to the R3 row, with respect to R1, I'll make it as R3 first element as 0, that is minus 7 and plus 7, this is 0, and next 2 plus 14, this is 16, and next minus 3 and minus 3 plus 7 5 is 35, that is 32. Okay, this is 32 into xyz as 0, 0, 0. Okay, here I am taking common for R2 divides 8 and R3 divides 16. That is minus 1, minus 2, minus 5, 0, 1, 2 and 0, 1, 2 into xyz is equal to 0, 0, 0. Here once we have to observe, here these two are similar, right? These two are similar. For that, I'll reduce as the third row complete as 0 with respect to R2. That means R3 tends to R3 minus R2. From that, minus 1, minus 2, minus 5, 0, 1, 2, 0, 0, 0 into x, y, z is equal to 0, 0, 0. Here once observe, now we have to write it as these two are, okay, these two are one equation form, and here from the first equation write it as minus x minus 2y minus 5z is equal to 0, and the second equation y plus 2z is equal to 0. Here we have to find x value. Okay, here two equations. From the two equation we have to find x, y, z values. From that I'm assuming one as arbitrary constant. Here I'm assuming either x or z are arbitrary constant. From that we get directly here. Okay, from that here we get directly, once observe here I'll assume as z as k. Z as k. From that, what about y? That is minus 2k. Y is equal to minus 2k. If you know that z as k, y as minus 2k, substitute in the first equation, that is minus x minus 2 into k minus 5 into k is 0. That is, once observe y as at plus, this is plus, minus x minus 3k is once observe here minus x, y is equal to minus 2k z as k. Here minus x plus 2k minus 5k, that is x as 3k. Okay, from that concept here we get directly one eigenvector form, that is x1. Okay, 1, so x minus 2 minus y plus 2z is equal to 0. Here we are assuming z as k. Okay, y as minus 2 and z as k. And what about this 2 into, okay, here 2 into 2k, right? Here 2 into 2k, that means is plus k. This is minus x is equal to k, that is x is equal to k. Okay, here x is equal to k and y is equal to minus 2k. X is k, y is 2k, minus 2k, and z as k. Okay, this is one eigenvector x1. From that I am taking common minus k, that is 1, 2, minus 1. Okay, from that I am taking common 1, minus 2, 1. So z as y as minus 2k means, okay, here this is minus, maybe here some mistake, is equal to minus 2k. And here minus x, this is minus. Okay, from that we get here 1 to minus 1. Therefore, whatever for the distinct eigenvalue, we get first eigenvector, that is 1 to minus 1. That is first eigenvector 1 to minus 1. Similarly, we have to find the repeated eigenvalue. What about the repeated eigenvalue here? Lambda is equal to minus 3. We have to apply the same concept for that. What about the concept here? Same. Okay, by using write it as the eigenvector formula a minus lambda I into x is equal to 0. For that same concept, if once observe, if the repeated eigenvalue, for the repeated eigenvalue in that one case only we get two eigenvectors. Okay, in one case only we get two eigenvectors. What about the two eigenvectors after using this concept, that is x2 is equal to 2 minus 1 0 and x3 is equal to 3 0 1. Already these concepts we discussed in the previous classes. Same concept here we have to apply. Why? Because it's very lengthy question, no? So that I'm going through the next step, so that here this concept is already discussed in the previous classes. Go through that concept. Here for the repeated eigenvalue as minus 3, according to these concept, in that one case only we get the two eigenvectors. What are the two eigenvectors here? The two eigenvectors are 2 minus 1 0 and x3 is equal to 3 0 1. Okay, na? Same concept for that. Okay, that means once observe, if the repeated eigenvalue is minus 3, for that in one case only we get two distinct eigenvectors. Sometimes we are not getting two distinct eigenvectors, but here we get two distinct eigenvectors in one case. That means these all geometric multiplicity is equal to how much? 2. 2. And the previous, after finding the eigenvector, that algebraic multiplicity is also 2. Therefore, AM is equal to GM, then definitely the given matrix as diagonalizable. After getting the eigenvectors, we have to verify algebraic multiplicity and geometric multiplicity. If the two are equal, then go through the next procedure, or else directly write down. If the two are not equal, then directly it is not diagonalizable. But here in that case, for the repeated eigenvalue, algebraic multiplicity and geometric multiplicity is equal, then the given matrix is diagonalizable. If you know that two are equal means, then go through the next concept of the diagonalization of a matrix. Okay, if the two are equal means this is diagonalizable. After that, if you know that two are equal means, write it as the corresponding eigenvectors P is equal to x1, x2, x3 as one model matrix form. Then matrix is called what? Model matrix. The matrix is called as model matrix form. This matrix is called as model matrix. Okay. P is equal to x1, x2, x3. Write it as x1, x2, x3 as column wise. What about that first one? 1, 2, minus 1. And the second one, 2, minus 1, 0. And the third one, 3, 0, 1. Okay. This matrix is called as a model matrix. Okay. After getting that model matrix, what about P inverse? P inverse is equal to adjoint P by det P form. Okay, for that I am finding the determinant of the matrix. What about the determinant of the? Okay, that is 1 into minus 1 into 1. That is minus 1 minus 0 minus 2 into 2 minus 0 plus 3 into 0 minus 1. From that, this is minus 1 minus 4 minus 3. This is directly equal to how much? Determinant of P value minus 8. Minus 8. Therefore, P inverse is equal to what? Adjoint P by det P. From that we get directly P value as 8. That is 8. One denominator value is equal to 8. And what about the adjoint of P? We have to find out each and every element minus. Okay. From that minus here, okay, write it as adjoint of P matrix form. For that one, that minor is minus 1 of 0. That is minus 1. And 2, that corresponding minor, 2 minus 0, 2. And next 3, that corresponding minor, 2 minus 1. That is minus into minus plus, that is 3. Okay. And next 2, that corresponding minor, that is neglecting the corresponding row and column, minus 1 and 1 minus 3, that is minus 2. And next this minor as 4 and this minor as 6. Similarly, minus 1 minor as minus 1 and 0 minor as minus 2 and 1 minor as minus 5. Okay, minus 5. And after that, write it as plus minus plus minus plus minus and plus minus plus. From that we get directly, that is minus 1 minus 2 3 minus 2 4 6 and minus 1 minus 2 minus 5. Okay, therefore what about P inverse? Minus 1 by 8 into minus 1 minus 2 3 minus 2 4 6 minus 1 minus 2 minus 5. This is P inverse. Okay, after getting the eigenvalues and after getting the eigenvectors, and we get here P inverse also. And the next concept, next step, P inverse. Multiply P inverse A into P. P inverse A into P form. Here, what about P inverse? Okay, adjoint P by det P form and A as the given matrix and a given question. And what about P matrix? This as the P. P as model matrix. Okay, P as model matrix. Multiply that 3. Okay, already we know that multiplication of a matrices. Okay, multiply that 3, we get directly one matrix form. Okay, after getting that matrix form, okay, if you are facing the difficulty for multiplication of the three matrices, for that case directly we have to apply the scientific calculators for multiplying the matrices. For that also we get the correct answer. Okay, if we are multiplying the three matrices, here we get directly 5 0 0 0 minus 3 0 0 0 minus 3. Once observe here what about the matrices. Okay, here once observe after the getting the diagonal matrix, once observe the diagonal elements. These diagonal elements is equal to what? The diagonal elements are equal to the eigenvalues of the given matrix. Once observe what are the eigenvalues here? 5 minus 3 minus 3. So that if after getting the diagonal matrix, the diagonal matrix elements are equal to the eigenvalues, so that the given matrix is diagonalizable. Therefore, this is the correct answer for the given square 3 by 3 matrix. Okay, this is the concept of the diagonalization of a matrix. What is the concept? First of all, write it as one square matrix. Once observe the given matrix as square, okay, from that we have to find eigenvalues, and after that we have to find eigenvectors, and for that write it as eigenvectors as one matrix form P. For that we have to find P inverse and multiply P inverse with A into P, okay, that is equal to D. Okay, if that is equal to D means that D is called as a diagonalization of a matrix or spectral matrix. In the diagonalization of diagonal matrix, the diagonal elements are equal to the given matrix. Okay, given matrix eigenvalues. So our answer is correct. So that the given matrix is diagonalizable. Now we are discussing what we discuss now. The given matrix eigenvalues are a repeated case. Okay, in that repeated case, we discuss the diagonalization of a matrix concept. Okay, next I'll discuss with another question. Okay, find a matrix P which transform the matrix A is equal to 1 0 minus 1 1 2 1 2 2 3 to diagonal form. Hence calculate A power 4. Okay, hence calculate A power 4. Here what they are asking in the question, they are asking two cases. One is diagonal form and another one is the calculation of the A power 4 form. Okay, here what about the solution? Same concept. Okay, same concept. For the given matrix, first of all we have to verify is it a square matrix or a rectangular matrix. This is square matrix, that is 3 by 3 matrix. For that, first we have to find the eigenvalues for the given matrix. Okay, for finding the eigenvalues, write it as one characteristic equation form. What is that characteristic equation form here? Okay, det A minus lambda I is equal to 0. For that, 1 minus lambda 0 minus 1, 1, 2 minus lambda 1, 2, 2, 3 minus lambda is equal to 0. For that, write it as equation form. What is the equation there? 1 minus lambda into determinant form. But from the determinant, we get one equation form. What is that? 1 minus lambda into 2 minus lambda into 3 minus lambda minus 2 minus 0 minus 1 into 2 minus of 2 minus lambda 2 minus 1 subsum minus 1 into 2 minus of 2 minus lambda, this is bracket, is equal to 0. After solving this equation here, we get how many eigenvalues? Here we get 3 eigenvalues. What are the 3 eigenvalues? Lambda is equal to 1 and lambda is equal to 2 and lambda is equal to 3. Okay, here once observe, here eigenvalues are distinct or similar. Here 3 eigenvalues are distinct. If the three eigenvalues are distinct means definitely the given matrix is what? Diagonalizable. Clear? Okay. Previously we discussed with the similar eigenvalues and now we discussed with the distinct eigenvalues. If the eigenvalues are distinct means definitely it is diagonalizable. So that we have to proceed the next concept of the diagonalization of a matrix. For that, if x1, x2, x3 be the components of an eigenvector corresponding to the eigenvalue lambda, we have, okay, we have, what is the formula for that? A minus lambda I into x. That is 1 minus lambda 0 minus 1, 1, 2 minus lambda 1, 2 to 3 minus lambda. x1, x2, x3 is equal to 0, 0, 0. Okay, for three eigenvalues, we have to find three eigenvectors. For that, first of all, I'll write it as one eigen matrix, a minus lambda I into x form. Okay, na? From that here, for how many eigenvalues? Three. For each and eigenvalue, we have to find eigenvector. For that, this is the formula. Here we have to first substitute lambda is equal to 1. Here we have to substitute first value as lambda as 1. 1 minus 1 is equal to what? 0. And next one, 0. And next one, minus 1. And next, 1, 2 minus 1, that is 1. And next, lambda is 1, 2 minus 1, 1. And 1. Next here, 2, 2, 3 minus 1 as 2. x1, x2, x3, 0, 0, 0. Okay, here after getting that matrix form reduced as echelon, for that we get eigenvector of the corresponding eigenvalue of lambda is equal to 1. For that we have to reduce the matrix as echelon with respect to the row operations. What about the concept of that? For that here I'll interchange the R1 interchange to R2. I'll interchange the row R1 to R2. For that, 1, 1, 1, 0, 0, minus 1, 2, 2, 2 into x1, x2, x3 is equal to 0, 0, 0. Once observe here, echelon form means what? Echelon form means below the diagonals are zeros. Here, what about the below the diagonals after interchanging the row? 0, 2, 2. And here on diagonal element also 0, no problem. Okay, now I am applying the row operations, okay, by reducing the matrix as echelon. Echelon means we have to reduce the below the diagonals are zeros. For that, what about the row operation? That is here directly R2 first element as 0. No need to take that row operation. Here I will take R3 tends to R3 minus 2R1. That is 1, 1, 1. 0, 0, minus 1, 2 minus 2, 0, 2 minus 2, 0, 2 minus 2, 0 into x1, x2, x3 is equal to 0, 0, 0. Once observe, now after using that R3 row operation with respect to R1, now the given matrix reduced as echelon. That means below the diagonals are 0. For that, now write it as equations form. What about the first equation? Here it is there. x1 plus x2 plus x3 is equal to 0. And the second equation, x3 minus x3 means x3 is equal to 0. From that here, for that three unknowns, we have to find three unknown values for the three equations. But here we get only one equation form and one eigenvalue of, x3, one unknown value of x3 is 0. Now we have to find two unknown values, x1 and x2. For that case, we have to assume either x1 or x2 as k. Okay, or else x1, if you know x3 as 0, substitute in the above equation x1 plus x2 plus x3 is equal to 0. From that x1 plus x2 is 0. From that x1 is equal to minus x2. So that what about the values for that? x1 as 1, x2 as minus 1 and x3 as 0. Or else if you are confusing with that, okay, we have to assume x2 as k. or else x3, x1 as k. From that also we get the same answer. Here we have possibility for substituting x3 as 0. From that we get directly x1 and x2 values. Okay, or else here we have to assume either x2 or x1 as k. From that also we get the same answer. So that here x1 is equal to 1 and x2 is equal to -1 and x3 is equal to 0. Therefore, eigenvector here x1, that eigenvector is equal to what? x1 as 1, x2 as -1 and x3 as 0. Therefore, 1, -1, 0 as the first eigenvector if lambda is equal to 1. Next, similarly, we have to find two distinct eigenvalues, eigenvectors. Same concept we have to apply with for finding eigenvectors a minus lambda I into x as 0. For that, okay, if lambda is equal to 2, okay, we get that matrix, eigenvector, that is -2, 1, 2. And if lambda is equal to 3, for that case eigenvector -1, 1, 2. Okay, same concept here we are applying. Okay, from that, therefore here, whatever the model matrix P has, x1, x2, x3. For that, whatever the first model x1, 1, -1, 0, and -2, 1, 2, and -1, 1, 2. This is called model matrix. After getting the model matrix, whatever the concept after getting the model matrix, next P inverse. Okay, finding P inverse. Whatever the form of the P inverse is equal to adjoint P by det P. For that, first of all, we have to find det P value for the P matrix and adjoint of P. Okay, after that we get, okay, after that same concept already we discussed in the last problem. Same concept here we have to apply for finding P inverse, that is adjoint P by det P. From that we get this matrix, that is 0, -1, 1 by 2, -1, -1, 0, 1, 1, 1 by 2. And the next, what about A matrix? This is the given matrix and this is P matrix, 1, -2, -1, -1, 1, 1, 0, 2, 2. Okay, therefore, multiply P inverse with A into P form. Here we get one matrix form. What about that matrix? 1, 0, 0, 0, 2, 0, 0, 0, 3. This is equal to what? One D matrix. Once observe, after getting the diagonal matrix, once observe the diagonal elements are equal to eigenvalues or not. Here the given matrix diagonal elements are equal to what? Eigenvalues. So that the given matrix is diagonalizable. This is the first case of the answer. In that continuation, what they are asking in the question, calculation of a power 4. What about the formula of the a power 4? A power 4 is equal to p into d power 4 into p inverse. Okay, that is, what about p? P means model matrix, that is 1, -2, -1, -1, 1, 1, 0, 2, 2. And what about d power 4? 1 power 4, diagonal matrix power 4, 0, 0, 0, 2 power 4, 0, 0, 0, this is 3 power 4, into what about P inverse? 0, -1, 1 by 2, -1, 1, 0, 1, 1, 1 by 2. Okay, multiply these three. Okay, multiply these three. For that case we get directly, okay, if you are multiplying with 3 is difficult, means for that case directly multiply with the scientific calculators, get direct answer for the a power 4. Okay, here what is a power 4 answer? That is -49, -50, -40, 65, 66, 40, 130, 130 and 81. Okay, or else scientific calculators are not available. For that case, what about the multiplication of the matrix? First of all, we have to multiply with 2. After getting this answer, again multiply with these two. Okay, na? After multiplying also, we get the same answer of a power 4. Okay, this is the concept of the diagonalization of a matrix. What is diagonalization of a matrix? Reduce the matrix as diagonal with respect to the formula of D is equal to P inverse A into P form. And what about the powers of the matrix? E power n is equal to P into D power n into P inverse. Okay, these are the formulas for reducing the matrix as diagonal form and calculation of A power 4. Sometimes they are asking directly from the matrix, find A power 4. How you got A power 4? Through the concept of the diagonalization of a matrix only. Okay, na? These are the concept in diagonalization of a matrix. Next class, we will discuss with some other topics in module 2. Thank you. Thank you for all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.